Good morning. Since we were snowed out of our first day of classes, I think what I'll do is I'll just have a short video that I'll put up about systems of linear equations. I'll keep things relatively simple for now, and we can get more sophisticated as we go along. The term linear equation originates from the same root word that gives us line. If I have two variables, x and y, and I think about all the places where 3x plus 4y is 12, then obviously by looking at the intercepts, I can tell you all about that straight line. More generally, if a, b, and c are constants, quantities that don't depend on the x and the y, my general linear equation with two variables will be constant a times x plus constant b times y equals constant c. If I have more variables, I'll have similar things. If I had an equation with three variables, x, y, and z, 3x plus 2y plus 8z equals 24 is a linear equation with three variables in it. If I find out where y and z were both 0, that would be x equals 8. If I find out where x and y are both 0, that would be z equal 3. And if I find out where x and z are both 0, that would be y equal 12. This is a small piece of the graph of this equation. It's a plane in three-dimensional space. Although I can't draw pictures in 4 dimensions or higher, we'll regard a linear equation as being something that's like a line in the two-dimensional plane, or like a plane in three-dimensional space. In higher dimensions, we'll often just call these things hyperplanes. If I have more than one of these linear equations, we say that we have a system of them when I want both of them to be true. A solution is a pair of numbers, x and y in this case, that make both of the equations true. Since the graph of both of these things are straight lines, in most circumstances, you'll have two straight lines that point in different directions and therefore will cross at a single point. The x and y coordinate of that point is your solution. In this particular example, I think it's pretty clear that these two straight lines are going to cross at the place where x is 2 and y is equal to 0. We'll check that just to be sure. Putting x equal 2 and y equal 0 into the first equation, I find out that I get a true statement. So x equal 2, y equals 0 is going to obey that first equation, but we haven't checked the second one yet. If x is 2 and y is 0, 4x minus y is going to be 4 times 2 minus 0, 8. And to make the second equation true, I'm supposed to get 8, which I do. I want to look at one more such example, a system of three linear equations with three variables. As we'll see, this substitution method that we're looking at will work, but it becomes increasingly cumbersome as the number of equations and variables increases. I'll solve the last equation for z in terms of x and y, and then I'm going to write down the first two equations, but every place where variable z appears, I'll write in 6 minus x minus y. In this particular system, I've lucked out because in the new version of the first equation, I have x minus x, and the x's cancel out. All it remains is y plus 6 equals 8, so that's immediately going to tell me what the y is. So I got lucky on this one. As another example, let's think of a system of three linear equations, but there's only two variables in it. On the face of it, it looks very much like there shouldn't be any solutions because I've only got two things to move around but three requirements. Whether that's true or not depends on the details. If I solve the first equation for y in terms of x, getting the y equal 3 minus x, and I put that into the other two equations, let's see what happens when I simplify. Bizarre though it may seem, there actually is a single x number, x equal 5, that will work here. Once I know that x equals 5, obviously y has to be negative 2, and this system of three equations with two variables has a single unique solution. Of course, I've just been playing a game on you. If you look at the system of equations, add the first two equations together, x plus 2x is 3x, y plus 3y is 4y, and 3 plus 4 is 7. If the first two equations are true, the third one is automatically true because it's just the sum of them. In fact, in this system, you could argue that if any one of the two equations has been In fact, you can argue that if any two of those equations are true, the third one is automatically true. So in a certain sense, there's a redundancy or dependence going on here. We'll get an official definition for linear dependence and linear independence later, though. Having gained a little bit of insight into what's going on in this system, it might be informative to think about this system. X plus y is 3, same equation. 2x plus 3y is 4, same equation. X plus 2x is 3x. Y plus 3y is 4y. 3 plus 4 is 7. So if I change this 7 to an 8, if these first two equations are true, the third one is automatically untrue. I can already tell you just by looking at this, there's not going to be any solutions at all. Maybe we should do the calculations and see that. Now, it's important not to get confused about this. Both of these equations have to be true at the same time if I'm going to get an x, y, and z out of this. In order to get a solution, x has to be 5. However, in order to get a solution, x has to be 20. X can't be 5 and 20 simultaneously. This system of equations doesn't have any solutions. You could also have fewer equations than the number of variables. So in this little example, I'm going to think of x, y, z, and w as being my variables. I want x plus y plus z plus w to equal 1. I also want 2x minus y plus 5z plus 2w to equal 0. Following the usual kind of plan, I'll solve, say, the first equation for w in terms of x, y, and z, and then write in that value for w into the second equation. This produces a very strange result. You get to pick z. You get to pick z to be anything you feel like it, and once you've picked that z, you automatically know the corresponding y. Once you know the z and the y, you know nothing about the x, so you get to pick the x to be anything you want also. So having done that, the w will be 1 minus x minus the appropriate y value minus z, where x and z can be picked to be any numbers you want to pick them. There is a 2-parameter family of solutions. There's an infinite number of solutions to this thing. And lastly, here, even though I have 4 things to move around and only 3 requirements, there's not going to be any solutions at all. If you add the first 2 equations together, you'll get 3x plus 5y plus 4z plus 3w equals 1 plus 2, which is not 4. If the first 2 equations are true, the third one is automatically false. That system of equations, even though it looks reasonable enough, has no solutions. So here's what we know so far. A linear system of equations, regardless of the number of equations or the number of variables, there's only 3 things that can happen. There can be one single set of variable values that makes all the equations work. That's what we mean by a unique solution. It's also possible the system of equations has no solutions at all, and it's possible that you have an infinite number of solutions, but not just any set of variable values will work. There's a certain structure to it. I think this is enough to get us started. I don't know what the weather is going to be like tomorrow, so be sure to keep an eye on that. Hopefully we will get to meet up Thursday. Otherwise, we will continue talking in this way. I hope everybody's staying safe. I'll talk to you again soon.